Hi everyone, these are your notes for our new Unit 5 on perpendicular and angle bisectors. And hey, before we get into the notes, I thought I would just let you look at the calendar real quick. So you had your test today. We're going to be doing 5.1 notes today, and then the homework tomorrow, and then 5.2. And you can see the calendar. So look at what the things that are coming up. You got a quiz next Wednesday. You're going to be getting a new AP problem, and those are going to be due on November the 20th. And then November 21st, you have a test. Then you have this entire week off for Thanksgiving. Now, what I want to just remind you of is if you're from one of those families that 5 days off just isn't enough and you're thinking you're not going to be here on Friday, you need to start making arrangements now about taking your test the day before and having that done before the Thanksgiving break. So just keep those things in mind. Quizzes, APs, another quiz, here's the AP due, and then the test right before Thanksgiving. Okay, so let's get into the notes. So it says, well, before we talk about example 1, I want to give you some vocabulary because there's this word equidistance right here. So equidistant is kind of just the way it sounds. It means that something that's equidistant is the same distance from two or more objects. Okay, so we're going to start off here by proving the perpendicular bisector theorem. And here's the perpendicular bisector theorem. It says a point on the perpendicular bisector of a line segment is equidistant from the endpoints of the segment. So what we're going to do is prove that that this point Q right here is the same distance, because it's on a perpendicular bisector, it's going to be the same distance from A as it is from B. Okay, so in general, that's what we're going to do. Now, let's talk about what our strategy is going to be for that. And first of all, I need to tell you what the givens are. They forgot to put those in here. So we have given that QM is a perpendicular bisector of AB. And then what we're going to prove is AQ is equal to BQ. So note, I didn't say congruent. If we put lines over here, that would be the congruent symbols. What we're proving is the distance. So distance is just the points. This is what we use when we're finding distance, and an equal sign. But having said that, we're first going to prove that these two are congruent. And so here's going to be our plan. Let's map out a plan. If we have a perpendicular bisector, then we know we're going to end up with right angles, right? And we know we're going to have congruent segments here. And we know that we can use the reflexive property to get this line segment congruent. So if I were to draw some auxiliary lines right here, we can prove that these two triangles are congruent. And then once we've done that, we can prove that these two lines are congruent by CP/CTC, and then we can prove that they are equidistant from one another. So let's do the whole proof together. So you're probably going to need 2 columns. I'm going to start here, and then we'll finish up over here. So let's start by drawing our auxiliary lines. So Now, mind you, I'm on this little iPad and don't have a straight edge, so I'll do my best. So we're going to draw AQ. Not bad, huh? And then we're going to draw, so let's start with that. Draw AQ, and we'll call that auxiliary line. Let's write statement reason. Okay, and then we're going to draw QB. And again, that's auxiliary line. Okay, so let's use our given here. We have QM is the perpendicular bisector of AB. And that's a given. So remember, when we're doing bisectors of segments, you have to go from bisector to midpoint to congruent segments. So we have to put our midpoint statement in there first. So let's see here. We're going to say M is the midpoint of AB. And then that's the definition of a bisector. And then we can say AM is congruent to MB. And that's definition of midpoint. Okay, now, hang on there. Okay, and now let's see here. We can say angle AMQ, which is this angle right here, is a right angle. And that is definition of, gosh, I can't write on this thing. I'm really sorry. Not doing very well. Definition of perpendicular. So remember, we had perpendicular right here. You always have to have the statement somewhere beforehand when we're proving something. So we have it in there. So definition of perpendicular, and then we can say angle BMQ is a right angle. And again, that's definition of perpendicular. And then, since they're both right angles, we can say angle AMQ is congruent to angle BMQ. And why is that? All right angles are congruent. And then, let's see here, next, we're going to talk about this line segment right here. We're going to say QM is congruent to QM, and that's going to be reflexive property of congruence. And so let's look at what we've got here. We have angles that are congruent right here. We got a side, and we have another side over here. So we can now say that triangle AMQ is congruent with triangle BMQ. And how do we know that? Side, angle, side. And so as a result of that, which I forgot to put my little marks right here on QM. Okay, and because of that, we can now say that AQ is congruent with QB. And how do we know that? CPCTC. Corresponding parts of congruent triangles are congruent, and so then our final statement on our proof is going to be that AQ, the distance, is equal to QB, distance. And how do we know that? That's definition of congruent segments. And so we've just proved the perpendicular bisector theorem that put a point on the bisector is going to be equidistant from two or more points, two or more objects. Okay, so there you go. And I should, what am I saying? Not two or more objects, but the two endpoints of the segment. Okay, it's getting late. Okay, so let's go on to example 2. Okay, so example 2 says, what is the shortest distance from this point P, notice point P right here, to each ray of this angle? So it should be rather obvious what the shortest distance is, but I thought I would just mention when I was a coach over at North, on Fridays, we used to have fun Fridays every once in a while when we need a little break from athletics. And we would play this game called Steal the Bacon. And we would line up all the girls on one side of the room and all on the other side. So we had 2 teams. And then we would put these objects that are right in the middle, and we called it the bacon. And then you would call out, the girls had numbers that they were assigned, and you would call out numbers to run, and the first one to grab the bacon and get it back to their team would win. Well, so what would be the primary place you'd want to be? It would be right here where where we have a perpendicular, because it's much shorter to the bacon from here than it is from these ends. So, it was always best to be right here toward the center, and if you wanted to win the game. So that's just to kind of share that the shortest distance of this point to these rays is going to be the one that creates the right angle, the perpendicular of that. So, having said that, we're going to look at example 3, and we want to prove the angle bisector theorem, and that theorem states, if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. Okay, so we're going to prove that, and let's talk about what our strategy is going to be. So I'm going to erase this, and let's look at our givens. First of all, they didn't give us a full drawing here. It says that PR is perpendicular to WR, so we have to go ahead and I'm going to draw that in, and we're going to put the R right there, and then it says PT is perpendicular to WT, so we're going to put that in and put point T right there. And so let's talk about our strategy. Shoot. Okay, so let's think here. We want to prove that this distance right here is the same as this one, RP to PT, or PR to PT. So we know that because we've been given that these are perpendicular, that we're going to be able to have right angles. So we know we can prove that. And we've already been told that this is an angle bisector, so we know these two angles are congruent. And then we know by reflexive property that this is going to be congruent. So we can get these two triangles congruent, and then we can use CP/CTC to show that these sides are congruent, and then we can prove that their distances are equal. Okay, so let's get to it. Okay, let's start with our given. WP bisects angle RWT. That's given. So we know that angle RWP is congruent with angle TWP, and that would be definition of angle bisector. Now, let's do our next given. PR is perpendicular to WR, and that's a given. And therefore, we know angle WRP is a right angle. And that's definition of perpendicular. And then we have PT is perpendicular to WT. And so that's given. So we know that angle TWP, or hang on a second, I want to write it the other way. We'll call it angle WTP is a right angle, and that's definition of perpendicular. And let's go ahead and draw those in. And let's see here. We can say now, we can go ahead and declare that angle WRP is congruent with angle WTP, all right angles congruent. And then let's go ahead and take care of our side right here. We can say PW is congruent with PW, reflexive property. Okay, I'm going to continue over here. Almost done. Triangle, because now we have an angle, and a side. So we can say triangle WRP, is congruent with triangle WTP, angle side, and let's just find it. Here's our side right here. Here's angle, and where's our other angle? Up here. Angle side. And so now that we know that, we can say that PR is congruent with PT by CP/CTC, and therefore PR is equal to PT, definition of congruent segments. Good? So there we've proved it. When you have an angle that's been bisected and you pick a point on it, it's going to be equidistant from the rays of the angle, or equidistant from the sides of the angle, I guess I should say. Okay, let's go to the back. Okay, it says on this graph, plot the points A, -1, 6. So we're going to do that. It's right up here. And that's A. And then B is 3, 4, right here. B. And then it says, write the equation of the perpendicular bisector of AB. So let's think about what that means. If we take AB and we connect it, we make a line. And again, I don't have a straight edge, so I'll do my best on this. If we want to get the equation of the perpendicular bisector, we'd need a couple of things. One thing is we would need to know the midpoint, because the bisector is going to be in the very middle of the line segment. So we need the midpoint, and then we would also need to know the slope of the bisector. And so in order to figure out the slope of the bisector, we need to know the slope of AB. Because once we know the slope of AB, we can take the opposite and reciprocal, remember that's perpendicular slope, and then use that slope and the midpoint to get the equation of the line. So let's work on that, okay? So first of all, let's get the midpoint. So to get the midpoint, we use our midpoint formula, x1 plus x2 divided by 2, y1 plus y2 divided by 2. So our points are these. So x1, -1 plus 3 divided by 2, and that equals 2 divided by 2, which equals 1. And then 6 plus 4 divided by 2 is 10 over 2, which equals 5. So our midpoint here is going to be at 1, 5, right here. That's the midpoint. So we got that. And now we need to figure out the slope of AB. So AB, the slope equals, and we can use the slope formula, which is y2 minus y1 over x2 minus x1. But since we have a graph, we could just do rise over run. We can see that it's -1 over 2. It's going down. So we have a slope of -1 over 2. So what's the perpendicular slope is going to be the opposite, which is positive, and then the reciprocal, which is 2 over 1. So from negative to positive and then flip. And so 2 over 1 is equal to 2. Okay, so we still need to find an equation for this, and voila, you remember from algebra, when you have a point and you have a slope, you can use point-slope form to figure out the equation of the line. So that's what we're going to do. I'm going to have to erase some of this so that we can do our math, okay? So our point was 1, 5, and we have a slope of 2. So we're going to use point-slope form, which is y minus y1 is equal to the slope times x minus x1. So y minus 5 is equal to 2 times x minus 1. So you get y minus 5 equals 2x minus 2. Add 5 to both sides, and bada bing, bada boom. Here's our equation. Y equals 2x plus 3. That is the equation of the perpendicular bisector to this line right here. So I'm not drawing it in there very well, but you get the drift, right? That's where it's going to be. Okay, I think that's it. Now, you do have another page on your lesson, which is constructions. And here's what I'm going to say to you about that. We will go over those in class tomorrow. Make sure you have your compass. And if you would like a refresher, go to mathopenref.com and you can watch how it does perpendicular bisectors. And you can also watch how it does angle bisectors. Be a good thing to do, good review before you get to class tomorrow. And yeah, I'll just leave it at that. So we'll see you in class. Bye.